To continue our discussion of material balance, we need to initiate a topic that is generally referred to as degree of freedom analysis. And to do this, we're going to need one very specific rule. And in this video, I intend to derive that. That rule is called the Gibbs phase rule. Phase rule here. All right. And what this is going to do is it's going to relate the degrees of freedom we have for an equation to the amount of components and phases within an equilibrium-esque system. Now, in order to do this, I think we need to talk about a couple definitions first. First, what is a degree of freedom? This is how I'm going to denote degree of freedom in this video if I ever end up actually writing it again. Here we are, degree of freedom. And what a degree of freedom is it is how many variables we may specify for a given system. For example, in basic algebra, you learned systems of equations, and you can obviously see how that is going to be important in our study of material balance. Now, given a system with some constraints, as engineers, it's often our job to solve that system by some sort of theory. In that, we can set up material balances for that system, and then from there, we can go ahead and derive how many variables we need to actually go out and measure or specify. So the degrees of freedom are the variables that we don't need to specify. Which really just means to measure, right? Awesome. Okay, so we defined a degree of freedom, and from here we need to go ahead and kind of talk about what this definition of chemical potential is. Now, I don't think this is something that is generally discussed in a first-year chemistry course. This may be more of a physical chemistry-esque topic. Chemical potential, and I'm going to be denoting it by mu in this video. What chemical potential tells us is it is a relation of basically Gibbs energy per mole. And the way that we're going to write that, we'll say it is equal to the partial derivative of moles times Gibbs free energy over or with respect to moles of some component given a constant temperature and pressure. Cool. So, from this definition of chemical potential now, and how we can see how that relates to our Gibbs free energy, we can start to derive this Gibbs phase rule. Let me start out with an example of some sort of system here. So here's our system, and let's just put in some amounts of phases here. Maybe we have two liquid phases and one vapor phase. And I'll call this vapor phase V, I'll call this liquid phase liquid A, and I'll call this one liquid B. So, in kind of relating, maybe we have multiple components to the system. Let's say that we have some amounts of water, and some amounts of benzene within this system, right? So all of these two components will exist within each one of these phases within this system. Now from here, we can go ahead and relate the chemical potentials of that system. And the way we can do that is by saying the chemical potential within one phase, maybe it's the vapor phase, is equal to the chemical potential of that same component. We can call that component, maybe this is for water, in the liquid phase. And then we can also say that component's chemical potential in the liquid phase is equal to that is equal to its chemical potential within the other liquid phase. And this is true because we are in an equilibrium. So, from here, we've already gone ahead and actually derived two equations. Now, you may note that you could also write the equation mu V is going to be equal to mu LB. However, obviously this is going to be redundant, and that's not going to count as one of the equations in our degree of freedom analysis. So, we know this will be true for every component that we decide to throw into this equilibrium system. For example, we can also say that this will be true for benzene in the vapor phase. Try to use my organic chemistry here to draw benzene. And we would also say the same for its liquid phase component. Its liquid phase in the liquid A will be equal to its chemical potential within the liquid B portion here. Now, as you may note, if we were to add, let's say, I don't know, acetic acid into the system, right, then we would also be writing more chemical potential equations to relate those two components. So we can really say, and this is how this is denoted in the Gibbs phase rule, that we're going to have C equations here, and we're going to have C equations here. Now, what does this really tell us? Well, we have two sets of equations, and the equations are related to the number of phases present within the system, right? It's going to be the number of phases, which I'll call P, minus 1. Now, and all of that will be multiplied by C, right? We will have C equations times the number of phases minus 1, and that will be the number of equations that we have. Now from here we want to talk about the number of intensive variables, and what I mean by that, intensive variables. These are variables that don't depend on system size. So things like temperature, things like pressure, those are going to be two of our system variables. So temperature and pressure are always going to be two intensive variables for our systems. Things like molar amount will not be. Same with things like mass. Those components would not be intensive variables. So what we need to do then is figure out what variables can we talk about that do not depend on the size of the system, and how can we relate that to our degrees of freedom. So we want to figure out the number of variables that we're really dealing with here, and we already said temperature and pressure are going to be two of them. However, the other thing that we can do is we can write mole fractions for each component within the system. I'm going to make this a little bit generic rather than writing out each component as I did before. And the notation generally done for this is using the letter I to represent any of the components. So we can say X, I, well, I guess since this is gaseous, it would really be a Y molar fraction, I, and then another Y molar fraction for maybe component J, Y molar fraction for component K, all the way up to all of the components in the system, right? And we could say the same for the liquid phase, so it would be X of, this would be the A, I, X, J, X, K, and all the way up to all of the components of the system. So we're going to have, again, another C variables there, and C variables here, and then C variables here. And again, the amount of sets of variables that we are going to have depends on the number of phases, and this time it's directly equal to the number of phases. However, there is a kind of special relationship in this set of variables here in general. And that relationship relies on the fact that these are mole fractions, or that all the fractions are going to combine to get 100%, or in this case, generally they're given in decimals, so that will be 1, right? Which means that if I have, say, almost all of the mole fractions, if I have every single one of them except for 1, I'm going to be able to figure out the last mole fraction based on the idea that I can use 1 and then subtract what I've already summed up to get that. And so from that kind of expression there, we can say that really the amount of variables that we need to actually specify here, or rather that we don't need to specify, would be C minus 1 for each one of these. From that, C minus 1, and we can multiply that by our number of phases, and then add 2. And that will give us our number of variables. Okay. Now all we have to do is zero out our amount of equations and our amount of variables, and then we will be able to come up with an expression for the number of degrees of freedom. So I'm just going to go ahead and take our number of variables term here, p times c minus 1 plus 2, and subtract from that c times p minus 1, and set that all equal to 0. Now, in actuality, this isn't equal to 0, it's equal to our degrees of freedom, and sometimes this will be written as f for the purposes of this equation. Now, from here, let's just go ahead and do some algebra. And we can go ahead and say PC minus CP is going to cancel out, and then we are left with C minus P plus 2 is equal to our degrees of freedom F. And that is our Gibbs phase rule. Now this is an extremely powerful tool that exists for every single material balance ever. And so that's actually a really fascinating technique, or I guess rather thought experiment, that was kind of conceived from the fact that there's no real worry in trying to determine how many variables to specify, because it's always going to go by this equation here for any mass balance. So let's go ahead and mess with this on two kind of little sample systems here. And the first one I think it's fun to talk about is water at the triple point. Water at triple point. Now, we want to know how many degrees of freedom will exist in a system for water at its triple point. And I think this one is a really good one to start out with, because intuitively we know that the answer is going to be 0, right? Obviously, since all of the systems are water, there's no worry in how many mole fractions we have, and that makes it, fairly easy to solve the system there. But let's go ahead and see if Gibbs' phase rule holds true for that. So degrees of freedom, we said, will be equal to the amount of components. Well, assuming we have pure water, we will just say that there's one component minus the amount of phases. It's at its triple point, so that will be 3 phases plus 2, and that is equal to 0. So that one works out for us perfectly fine. Now, let's talk about when vapor and liquid coexist. So now we just have vapor and liquid. It's not just the point. So I'll say water with only vapor and liquid phases. And I would say this is probably the most common water equilibrium that we're going to experience in life, right? So the degrees of freedom, again, will be equal to number of components. Let me put that back in frame. Number of components, well, we only have water. minus the number of phases. Well, we only have 2 phases, vapor and liquid, and plus 2, and that is going to be 1 degree of freedom. Now this one may seem a little bit more less intuitive to you. However, I encourage you to think of the pressure liquid, oh boy, the phase diagrams that we initially discussed in these videos. And from that, for water, right, we drew basically this, and we said this was going to be vapor, this was going to be liquid, this would be solid. And then now we can kind of see where these graphs, or how this phase rule corresponds to these graphs. At the triple point, we said there were 0 degrees of freedom. I can't move anywhere. I'm stuck directly on that point if I am interested in obtaining that point. Then I have to stay exactly at that temperature. I guess this would be, I should label my axes there, temperature and pressure. I need to stay directly at that temperature and directly at that pressure. However, if we have liquid and vapor phases coexisting, it just needs to be somewhere on this curve. So I have, as a line is one-dimensional, right? I have 1 degree of freedom with which to move along that line. So at any temperature and pressure that exists on this line, I will be happy. In the sense that I have gone ahead and found our vapor and liquid phases. So that's a 1-component system. What happens when we add multiple components? So now let's talk about ethanol and water. Ethanol and water, and let's go ahead and just say that they have vapor phases and liquid phases here. I just 2 coloned there, I'm very sorry for my incorrect grammar. So again, degrees of freedom, ethanol and water, we now have 2 components, and from that we want to subtract our 2 phases, vapor and liquid, and then add 2 where those 2 constraints are going to be our temperature and pressure, and we will be left with 2 degrees of freedom. So you can see how this is absolutely useful, right? If we were to set up some system, we are now constrained with how many variables we can actually specify, right? There has to be at least 2 in this system of, let's say it's some sort of ethanol, water, I don't know, very least beaker, if on a larger scale tanker, right? Where I have a vapor and I have a liquid phase, and I have some mole fraction of water, some mole fraction of ethanol, and then I have the same up here, I'll just call it yi, yj. Now I cannot actually determine all of these mole fractions. I can't specify all of them if I want to specify some temperature and some pressure of this system as well. So I think this is a very useful tool, and we are going to use this relationship in the upcoming videos to do some more difficult or complicated energy balances. Thanks for watching.